Properties of elements and compounds. So we're going to do a little descriptive chemistry in this lesson, and we're going to go through and remind ourselves of where the metals, nonmetals, and metalloids are, and then talk about the different types of compounds we can form and some general properties of those different types of compounds. And then we're going to go back through and talk about a few of the groups on the periodic table, like the alkali metals, alkaline earth metals, the halogens, the noble gases, and just talk about some common trends in their chemical reactivity. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. You can find those courses at chadsprep.com. Now, this is part of my new general chemistry playlist. I'm releasing these lessons several a week throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel, click the bell notification. So let's dive in, and the first thing we're going to start with is just going back and reminding you of where the metals and the nonmetals lie on the periodic table. And a lot of periodic tables actually have like a thicker line right here that forms a staircase going down the periodic table, and that separates the metals on the left-hand side, which is the majority of the elements, to the nonmetals on the upper right-hand side. And then it turns out about a half dozen or so right along that staircase we call metalloids or semimetals. And that usually includes boron, and then silicon, germanium, arsenic, antimony, tellurium. And some people, may throw one of those out or include an extra or something like that, but pretty good consensus on those six for a lot of textbooks. Cool. And so it turns out we want to divide them up that way because we can talk about some different characteristics of metals, and whether you've got a pure metal, like just pure iron, or maybe whether you've got something like steel, which, we'll put some other metals in there with it, or maybe brass, which is a combination of things. Whether you've got a pure metal or an alloy, they're going to have some key characteristics. And so we want to refer to these then in general as metallic substances, whether again it's a pure elemental metal or whether it's a combination of metals and an alloy. And some of the properties you're going to see there is that they are good conductors. So, and it turns out they're good conductors of both heat and electricity. So, in the case of being good conductors of electricity, so it turns out the valence electrons are loosely held throughout a metal. So they don't really, belong to any one nucleus. They're kind of like community electrons, and it's those community electrons that are loosely held that allow the flow of electrons through the metal, the flow of electricity. So sometimes we call that the sea of electrons model, but that's what makes metals a good conductor of electricity. You contrast that with the nonmetals up here, and the nonmetals are not good conductors of electricity. They're insulators. So, if you're looking at, wearing some rubber shoes or rubber gloves to be insulators because you're working on electrical lines or something like that, they're typically, rubber's a hydrocarbon, and carbon and hydrogen being nonmetals, so make good insulators. Okay. And then you got the semimetals or metalloids here right in the middle again, which are semiconductors. So metals are conductors, nonmetals are not. The semimetals are semiconductors. Notice the heart of the semiconductor industry is silicon here, one of these semimetals or metalloids. Some other properties of metals you should know, though, in addition to being good conductors of heat and electricity. So some key buzzwords we do expect you to know is they have a characteristic luster. So that is not common among some of the other substances we'll talk about. And so luster means that they are shiny, and metals tend to be shiny. Okay, so some other words you'll see here is metals are malleable. So and malleable just means you can pound them in different shapes, and you can pound them out into sheets and stuff like this. And this is a word we sometimes use, having a coworker who is malleable is a good thing because they can kind of adapt to the situation and work with whoever and things of this sort. So, and then the last one here is one you're probably not going to use in any other context, and that's the word ductile here. And this is a property of metals that means that they can be drawn into wires. And notice all your lovely metal wires are all your lovely metal wires are made of metal. All your lovely wires are made of metal. Of course, all your metal wires are made of metal as well. So, but again, that's the property ductility here. And so malleability or malleable, ductility, ductile, these are all properties you should associate with metals. And again, whether it be a pure metal or an alloy. All right, so now that we know where all the metals and nonmetals lie, just want to review the different types of compounds. And so if you could take one of the metals and combine it with one of the nonmetals, you're going to get an ionic substance. So, and there's a couple things you should definitely know about ionic substances. And so one, they tend to have very high melting points and boiling points. So it turns out if you want to actually melt or boil an ionic compound, you are breaking some portion or all of the ionic bonds. And breaking bonds takes a lot of energy and a lot of heat in this case. So if you want to melt like salt, like sodium chloride, you're looking at like, 800 degrees Celsius. And if you want to boil it, I think you're somewhere up around 2000 degrees Celsius. So super high melting points and boiling points for these salts. And what's going to be weird though is that we often associate them as being brittle. And that seems kind of counterintuitive because you're like, well, wait, they take super high amounts of energy to melt or boil because they're held together by these strong ionic bonds. So how does that mean that they are brittle? So we'll think about having a big salt block, and I don't know if you've seen one of those big salt licks they give to horses. It's just a big cube of salt. Well, imagine hitting that with a sledgehammer, and it would shatter into a million pieces. Well, notice that's not going to happen if you hit a big piece of iron, metallic iron. You hit a big piece of iron like an anvil, and it might pound, and depending on how malleable it is, it might allow you to change its shape, but it's not going to shatter into a million pieces because metallic compounds are not brittle in the way that ionic compounds are. And what's really going on here, so if you look at an ionic compound, you've got cations and you've got anions here, and we'll just alternate them all the way across here. Put a couple of different rows here, and this is going to get expanded out in 3 dimensions. But what you find is that every cation is only going to be surrounded by its nearest neighbors by anions, and every anion, its nearest neighbors, are all going to be cations. Well, what happens when you hit that salt lick with a sledgehammer is you're going to cause these rows. You're going to put a stress on this, and you're going to shift the rows over a little bit. And if you shift the rows over, you might move this one over to the left a little bit to where it's surrounded by all anions instead of cations. And again, as long as he's surrounded by all cations, it holds the entire substance here together, the whole crystal together. But once you shift this over a little bit, all of a sudden now you get a repulsion from all your nearest neighbors, and it fractures all along one layer. And that's what makes them brittle, is you put any kind of stress on them, and instead of attractive forces with your nearest neighbors, you end up potentially with repulsive forces with your nearest neighbors. So definitely want to know that your ionic compounds are brittle. And then we'll talk about lattice energy. And this lattice energy is proportional to the charges. And then inversely proportional to the distance between the charges squared. So it turns out that the more positive and the more negative your cations and anions, the stronger the attraction between them. And then the closer they are, which usually means smaller ions, the stronger the force between them. And a measure of that's going to be the lattice energy, and we're going to see that in chapter 8 again. But I just wanted to pay a little bit of lip service that we often describe these ionic compounds, how strong the ionic bonds are between them, with this characteristic lattice energy, which again is proportional to the absolute value of the positiveness of the cation. So +2 would be a stronger attraction than +1, +3 stronger still. Same thing with how negative the anions are as well. -2 will have a stronger attraction than -1. And then again, the size of the ions matters as well, because you want them to be as close as possible, because the smaller that value of R, the higher the lattice energy, the stronger the ionic bonds. And again, we will cover this in more detail in chapter 8 here in the next chapter. Cool, so that's ionic bonding and ionic compounds. But what if we mix nonmetals here? Well, it turns out if we mix nonmetals, there's 2 different ways this could work. And one of the ways is we could form, if I can spell it correctly, molecular compounds. And the vast majority of the combinations of multiple nonmetals are going to be molecular compounds. They're going to form discrete molecules. So they don't form big crystals the way ionic compounds do. And it turns out metallic compounds tend to form big crystals as well. But molecular compounds are not going to form crystals in quite the same way. Now, if you freeze them, they will form into a crystal and stuff like that, but what holds those crystals together will not actually be bonds. It's not going to be ionic bonds. It's actually not going to be covalent bonds either, and it's not going to be metallic bonds holding them together. It's not going to be bonds at all. It's going to be these weak attractive forces that we'll talk about in the next chapter. And but it turns out, as a result of molecular crystals, when you freeze them anyways, the molecular solids being held together by these rather weak forces, it turns out they're easy to melt as well as boil. And so these tend to have low melting points and boiling points relative to the other types of substances that are out there. And again, there's exceptions to everything. I mean, metallic compounds, you're probably thinking of most of those having rather high, melting and boiling points. And notice we didn't really talk about them because there really is a spectrum. Like if you go over here to cesium, if you were, if you were foolish enough to play with some, it would melt in your hands. Its melting point is right around your body temperature, and so it could melt right in your hands and stuff like this. Whereas iron obviously has a rather high melting point and boiling point. So with metallic compounds, there's a pretty good spectrum of melting points and stuff like that. So we didn't really talk about it, but for ionic compounds, almost all of the ones you're ever going to see are going to have super high melting points and boiling points. There are exceptions, just none you're probably going to see in this class. So same thing with molecular compounds. The vast majority are going to have much lower melting points and boiling points than the ionic compounds we'll see. And again, there are exceptions. You can actually get some molecular compounds, some rather large ones that actually have pretty high melting points and stuff like this. So, but again, relative, just by comparing this class of compounds to this class, higher, lower, kind of the way we're looking at that. It turns out the other kind of combination of molecular compounds, of nonmetals you might see in addition to these molecular compounds are what we call a network covalent solid. That'll be our fourth type of substance here. And so these are few and far between. And so it turns out it's going to be a combination of nonmetals. And it doesn't have to be a combination, as we'll see, but it's going to be all made of only nonmetals. But it is going to form a crystal lattice structure and be held together by covalent bonds, not just the simple weak attractive forces. And so most notably, you're going to see things like diamond, or quartz, silicon dioxide here. One way of writing quartz. And so these are the most notable examples with no metals involved of these network covalent solids. So again, the vast majority, though, are going to be molecular. So if you think of things like water and carbon dioxide, these form little individual molecules that have a discrete number of atoms. So one water molecule has 2 hydrogens and an oxygen. One carbon dioxide molecule has 1 carbon and 2 oxygens. Well, these don't form molecules. One diamond has a ton of carbon atoms, not just 1 carbon atom. It has a ton of them, and the bigger the diamond, the more it has. Same thing with silicon dioxide. So the bigger the quartz crystal, the more silicons and oxygens there are. Now, they're always going to be present in a 2-to-1 ratio for oxygen to silicon ratio, but there's no such thing as a silicon dioxide molecule. So they're not molecular compounds, they form crystals instead. So just want to make sure you see this difference, but these crystals are held together by covalent bonds. And again, to melt or boil them, you will have to break those covalent bonds, at least some portion of them in the melting process. And so as a result, these tend to have fairly high melting points and boiling points as well. Cool. If you have ever tried to melt a diamond, because, we all try to do that, right? But if you tried, you probably would not succeed. So you probably don't have access to what you would need to actually melt a diamond or a piece of quartz or something like this. So super, super high melting points and boiling points. And in general, these probably have higher melting points and boiling points than any of the ionic compounds you'd probably take a look at as well. Cool. So these are our types of substances and some, really basic properties that are kind of give us some repeating themes in them. So, but now we want to go back and take a look at some of the different groups on the periodic table and just talk about some of the properties of the elements within those groups. And we're going to take a look at 4 of them in particular. We'll look at the alkali metals, the alkaline earth metals, we'll look at the halogens and the noble gases, and we'll take a quick look at oxides because they tend to get a little bit of press as well, and maybe just a brief look at sulfides as well. So we'll start with the alkali metals here. And so it turns out the alkali metals are known for having very low ionization energies, which we studied earlier in this chapter. And so they will, if you want to remove an electron from an element, picking an alkali metal is probably your best choice. And it turns out it gets easier to remove an electron as you go down again, as we kind of showed with our trend in first ionization energy a couple lessons ago. Now, it turns out that low ionization energy is going to have some profound effects. So one, it means they're going to combine with nonmetals very readily to form ionic compounds. Okay. But it's also going to mean that they're going to be highly reactive with water. So if you take a look at like the reaction between sodium metal and water, you're going to find out that it's going to liberate hydrogen gas in the process and make some sodium hydroxide. And if we balance this, so we'll see that we can get 2 of these here, 2 of these here, and I think we should be good to go at that point. Let's see. We got, actually, we're going to need another water molecule here too, aren't we? Let's see. So we got 4 H's, we got 4 H's, 2 oxygens, 2 oxygens. Yeah, we're good to go. So it turns out that alkali means basic in terms of like acidic and basic. And so the alkali metals are called alkali metals because when you combine them with water, it forms a hydroxide salt, an aqueous hydroxide salt. In this case, sodium hydroxide is one of your strong bases. We learned about it with the strong electrolytes. And so that's why they're called the alkali metals. When you combine them with water, it forms a highly basic solution, and it gives off some hydrogen gas, and they're highly exothermic. And you know, if you have a highly exothermic reaction releasing a lot of heat, when there's hydrogen gas around, good chance it's going to form some flames, igniting that hydrogen gas. And so it turns out these are the explosive metals, if you will. And it turns out they actually get more reactive with water as you go down the group, again, as they get lower and lower ionization energies. So, but it turns out if you keep any of these metals, if you use them, say, in your chemistry lab, you have to put a special sticker on your door, and that sticker is for the fire department. If they ever come to fight a fire in your lab, they're going to be looking for that sticker, and that sticker says that, hey, I keep some of these explosive metals in my lab, and so if you come to put out the fire, don't use water, because if you spray water on them, you're going to make the fire worse. So they will use something other than water to put out those fires in those labs. Cool, so that's the alkali metals. Next up on the list are the alkaline earth metals. And the alkaline earths, notice alkaline again means basic, alkali, alkaline, same diff. And the alkaline earth metals here, they're not quite as reactive as the alkali metals with water, but they're still pretty reactive with water, especially some of the large ones. They get more reactive as you move down as well. So like barium's pretty reactive with water, but not nearly as reactive as the alkali metals. Their ionization energies are not nearly as low as the alkali metals. But again, some of the big ones still pretty reactive, and that's probably what you want to know about those alkaline earth metals. Cool, so move to the other side of the table here, and I'm going to skip over to the noble gases, and the big thing you should know about the noble gases is that they don't do much. They're known for being chemically inert. Let me put that word on the board. So chemically inert, and this just means chemically unreactive. So there are very few chemical reactions that will ever involve a noble gas. And it turns out for the small ones like helium and neon, they don't do any chemical reactions at all. No chemical reactivity whatsoever. Now it turns out for some of the bigger ones, turns out if you react them with a very electronegative element, most notably fluorine, there are a very small number of chemical reactions and substances that you could form with them that are possible. But in general, again, the noble gases are known for being chemically inert. They just don't do a whole lot as far as chemical reactions go. And I'll find out in the next chapter that it's due to them having a filled octet, the perfect number of electrons and things of this sort. All right, so then we'll move on to talking about the halogens here. So in the halogens, so in the same way that kind of the alkali metals and then the alkaline earth metals were known for having relatively low ionization energies and readily forming ionic compounds with nonmetals, in contrast, the halogens are known for having fairly high electron affinities. And remember that when I say high electron affinities, I mean very negative electron affinities. If you recall, chlorine has the most negative electron affinity. As a result, they're known, in contrast, for combining with metals very readily to form ionic compounds. In fact, if you mix sodium metal with chlorine gas, they will react explosively with flames and stuff to form salt. It seems kind of weird that something as mundane as salt, if you form it from its individual elements, it is a highly exothermic reaction that, again, will typically give off flames and things of the sort. So kind of stunning to see something so mundane form in such a way. But that's what you should definitely know about the halogens. Again, just high, very negative electron affinities and readily combined with metals to form ionic compounds. Now, if we look at the chalcogens, and that's not usually a name you need to know, but oxygen's group technically does have a name called the chalcogens. And I only want to pay lip service to a couple of things. So one, sulfides. Sulfides are very insoluble. They're some of the most insoluble ionic compounds we know of. So mix any of these transition metals with sulfur as a sulfide, and you're going to form an insoluble compound. Now, it turns out that the alkali metals tend to form soluble sulfides, and ammonium tends to form soluble sulfides, but they're few and far between. Almost any other metal you combine with sulfur as a sulfide is going to be an insoluble compound. So things like, MnS, manganese sulfide, very insoluble. Copper sulfide, either Cu2S or Cus for copper 1 sulfide and copper 2 sulfide respectively, very insoluble. So lots of insoluble sulfides out there. And then finally, I want to talk about oxygen ever so briefly. So oxygen, it turns out that the most stable form of oxygen is diatomic, and you probably learned that once upon a time, even probably before you took general chemistry, but we did briefly talk about it at the very beginning of this course. And so the most stable form of oxygen as an element is elemental O2, diatomic oxygen, but it actually exists quite prevalently in the Earth's atmosphere as O3, which is ozone as well. And when you have an element, notice these are not compounds, an element having more than one elemental form, we use the word allotrope. And so O2 here and O3 are allotropes, and there's not really a whole lot of great places to bring up this word. I think I hinted at it in one other place and stuff, but it turns out carbon is another substance that forms allotropes, like diamond versus graphite. They're both forms of pure carbon and pure solid carbon, and they're allotropes. So, but here oxygen has two major allotropes, so O2 and O3, and again, the most stable of the two is the diatomic version. It's the standard state. So, and the other thing I want to talk about, though, are forming oxides. And you can form metal oxides and non-metal oxides. And so metal oxides might be something like sodium oxide, whereas a non-metal oxide might be something like carbon dioxide. And so it turns out that metal oxides tend to be basic. You put this sodium oxide in water and the solution is going to be a base. We'll find out that that would mean like the pH will end up being greater than 7 far down the road. And you can kind of see why that is if you actually show the reaction with water. And just like when you put sodium metal in water, you get NaOH, you're going to get sodium hydroxide here as well. All right, so that's metal oxides, so they tend to be basic. And then your non-metal oxides, like carbon dioxide. So if you notice, a lot of your pollution gases like nitrogen dioxide and carbon dioxide and sulfur trioxide. So those pollution gases are in some measure responsible for acid rain. And when you combine them with water, you form something acidic. And so it turns out carbon dioxide in water forms carbonic acid. And so if you take some pure water, let's say you got your hands on some pure water, and then you take a straw and put it in there and breathe through that straw, blowing bubbles into that water for a couple of minutes, you'll find out that the pH is no longer 7, which is neutral pH. The pH will now be lower than 7 because you've made that solution a little bit acidic by some of the carbon dioxide coming off your breath and dissolving that water to form some carbonic acid. Cool. So metal oxides, again, are basic. Non-metal oxides are acidic. And that's going to conclude what I wanted to talk about as far as some of the chemistry and descriptive chemistry of some of the groups here. Now, if you found this lesson helpful, consider giving me a like. Best thing you can do to make sure YouTube shares this lesson with other students as well. And if you're looking for general chemistry practice, quizzes, chapter tests, practice final exams, final exam rapid reviews, then check out my General Chemistry Master course. I'll leave a link in the description. A free trial is available. Happy studying.